Okay, it's fine. All right, we're recording now. It's recording now. All right. Aluminum PCBs for I think aircraft because if you want to save every ounce you can get, that FR the what do you call it? The dielectric is actually too heavy, so they make them out of aluminum to make it even lighter. So aluminum PCBs, flexible PCBs, or the classic standard rigid PCBs. The material they call it is FR4, stands for flame retardant 4. It's like a chemical that just basically doesn't catch. So it's very useful for these kind of things. Finally, one important aspect of your PCB is actually the thickness of that copper layer. If you have a thicker copper layer, that means the conductors are wider. It lets you handle more current. So if you're doing PCBs that they're supposed to handle a lot of current, things like motor drivers, things like power regulators, sometimes you might want to make the copper thicker to handle more of that current. But we'll go into that a little more once we start actually building these PCBs. Click. All right. Some quick PCB terms before I start, using Altium, just so everyone's on the same page. Like I said earlier, a via is basically a drilled hole through a PCB. It lets you connect different layers together so that you can have those more complicated connections. As you can see here, that's what a via on the PCB actually looks like, literally a hole, right? So additionally, if I move this bottom portion, sometimes you want to use a via to connect your top layer to ground. But there's a new technology that they're having. I say new, but it's like 20 years ago, where you can actually put the via inside the copper so you don't need that whole trace right. Speaking of traces, when I say trace, I mean like a wire. When I say trace, think wire, right? A trace is just that thin line of copper that connects components together. So when I say trace, think wire, right? Think wire, think trace. Cool? Cool. Any questions so far? I know I'm going a bit fast. No? Okay, cool. And don't be afraid to ask questions, though. We have a lot of time today. Yeah, shoot. I don't know. Please download it now. Hopefully by the end of the presentation. Oh, okay, that's good then. Yes. Although, did you also get the student license too? Okay, then yeah, hold on tight. And this will be recorded, so if you're not able to get it downloaded, you can just sit tight and watch for now. And if you want to do it on your own, you can follow along on the recording. Cool. Cool. All right. More terms for the PCB. While it's nice to have the connections, we need to be able to manufacture these, right? So there is a layer on the top of the PCB they call the silk screen. What it is basically it's like kind of decorative ink they put on top of the PCB, and it lets you mark where components are going. So for example, there's like a capacitor here. They marked it C3, 100 nanofarad, and they drew an outline in white. That's the silk screen. It can be really useful when you're manufacturing. This example is really good. You see a diode. The diode has it's like a front end and a back end, right? Cathode and anode. You can actually mark on the PCB where exactly the cathode should go. It helps avoid confusion, makes it easier to manufacture, right? There's also some pretty crazy things. If you actually look up PCB silk screen art, there's people that do just like crazy stuff with like silk screen. They can like draw all sorts of really cool stuff on their PCBs. So that's actually something we can do in Altium as well. But main thing to note is that the silk screen is decorative, but it's also really useful for labeling your components and marking the footprints on where they're going. Shoot.
If you sent a PCB to like JLPCB with silk screen art all over it, would they charge you extra for that, or is that so cheap that they don't care?
They don't actually, they're fine with it. Because on one of the boards that we made, I did do that. And they were like, okay. As long as it's within their manufacturing capability, they don't. And we'll go into that once we start actually talking about manufacturing. The PCB manufacturers can only make so tight of a tolerance, right? They can only make their traces so thin. So if you tell JLC PCB to make like an infinitely thin trace, they're not going to do it for you, right? So there's a bit of manufacturing that goes into that. But yeah, that's okay. Another key term to know is a footprint. You might have heard me say footprint a couple times, but a footprint is basically how the component is going to be put onto the board. So for example, this diode, the footprint would consist of these two holes, where you got to slot the diode into, right? for this chip here, the footprint involves all of these different paths where all the legs are kind of going to be soldered onto, right? So having the footprint of each component is essential to actually building the piece. Finally, last term, it's an electrical term if you've taken 1101, is a net. A net just means it's a shared electrical node. So if two things are connected to each other, you can call that a net. You might be familiar with the ground net, where if you build a circuit, everything's connected to ground. You can think of that whole connection as a net. Basically, it just means they're connected together, like a conductor, right? There's a lot of markers. Okay. So for an example, if you had a resistor here, and a resistor here, you could say that all three of these resistors are connected by this net. Maybe call it like N1. Now it's coming back to y'all. Y'all have done Thevenin, or was it node analysis? It's a net or a node. You can call it a node if you want. All right. Next thing is, well, we talked about the footprints, but what about the actual components? Nice thing about electrical components is that since PCBs are so like ubiquitous, they're everywhere, that these manufacturers have actually designed their chips to fit onto PCBs. So there's two different ways, as seen on the top there. There's a surface mount, a surface mount component, where all they have is like a pad. So if you go back a bit, like these would be surface mount. There's no hole drilling into the PCB. It's just placed on top. And the solder is going to just envelop and connect the pad to the component itself. Contrast that with a through-hole component, probably what you've seen on your breadboards. The breadboards are through-hole. It's literally a hole, and you're slotting into the PCB. Basically, you're slotting it into a via, and you're soldering basically the via and the pin together. Right? A nice thing about manufacturing is also they come in a lot of standardized packages. So if you have a bunch of resistors you want to make, you can actually look up a certain size, for example, a 1206 package, and actually you can keep all the footprints exactly the same because it's all standardized, right? So there's a couple common footprints package sizes that you'll see, especially for the ICs. You'll see things like SO8s, SOTs, DIPs, DIPs. If you've seen those logic chips from 2300, those are DIP packages. Yeah. So PCB components. Now, obvious segue. Where do we buy these components, right? You don't go to Target. Actually, kind of could. Main thing is we like DigiKey. DigiKey and Mouser are two websites that have a lot of different components. They work with manufacturers to get these components into consumer hands, right? So we can just buy off DigiKey. Some other websites include Jamico, UT Source, and often the manufacturers will also will allow you to buy parts from them as well. Yes.
Until you made this a long time ago, because Radio Shack.
Well, no, I actually made this like 2 hours ago.
Oh.
And also 20 years ago, you used to also be able to buy parts from Radio Shack. Not anymore, but because was it you needed to be able to repair like your musical equipment, like your instruments, and those use things like diodes, pots, that sort of thing. So Radio Shack. Also Amazon, if you like the 2-day shipping, if you have Amazon Prime, Amazon's also pretty good place to buy electrical parts, although your mileage may vary. Sometimes they'll just sell you crappy parts, right?
Oh, I noticed with Amazon also, the limit is that you often can't buy one type of part. You have to buy like every potentiometer value from 100 to 10,000, 10 each. And
Yeah.
they'll give you like a kit with like all the values. If you just want one specific thing, you're gonna have a hard time.
I'll actually tell you exactly why that happens. It's because these manufacturers, they just buy the parts from DigiKey in bulk, so it's cheaper. They pack them up into your little kits and they sell it to you at a premium. So actually, if you want to get the best deals, go to a DigiKey, but you usually have to buy in bulk. So often you'll see like a capacitor. If you buy one capacitor, it'll cost $1. But if you buy like 50 capacitors, the whole thing costs like $5. It's like a weird thing you got to get used to, especially when you're buying these things, is like when you buy in bulk, the price just drops. So yeah. Sometimes it's actually cheaper to buy 10 instead of like 3, which is really weird. Anyway, on to actually designing PCB. Now we're getting into the meat of it. The way we design PCBs is using something called EDA, or electronic design software. or design automation software. You may have heard of CAD, computer aided design, similar idea. This is like electrical version of it. So other EDA software, some of you might have heard of, KiCad or KiCad, I know you pronounce it KiCad, Easy EDA, Tinkercad, and Eagle. Eagle is one that's very classic. But Altium is used a lot in industry. I will say that. It's actually, if you're able to put Altium on your resume, makes you look really good. And also a lot of projects on campus also use Altium too, because we get it for free as students. So KiCad is also another good alternative. It's actually free and it's also open source too. So if you want to do like hobbyist stuff outside of school, KiCad might be would be a good thing. But Altium is what we're learning today. So now let's talk about why do we care about PCB design? It can't be that hard, right? You just got to slap the components together, right? It's just that easy. Unfortunately, it's not that easy. There's a lot of things that differ from your simulation versus the real world. So you might be able to run your circuit in PSpice and it works perfectly, but if you don't design it properly on the PCB, it can actually fail. So one of the things you run into are things called parasitics. Parasitics are basically unintended electrical characteristics. So your ideal wires in the simulation actually have resistance. Copper has resistance, a little bit, a couple milliohm, but it still has resistance. Your components, your ideal capacitor is actually not an ideal capacitor. It's a real capacitor. So you'll run into a lot of issues with that. So if you don't choose your parts correctly, if you don't design your board properly, you'll have a lot of parasitics that will actually cause your real circuit to fail, or at the very least have a different behavior than your schematic. So that's why learning this stuff matters. And it's also why this is such a very deep field. We learn about it now. I'm going to teach you guys now. It's going to be super easy, super simple. But if you really want to start doing better stuff, higher performance, higher frequency, it becomes a lot harder to lay everything out properly. So that's like, why do we care about PCB design? It's an entire field. You can get a job as just a PCB, not even a PCB designer, just being the one that does the layout, just like or arranging everything together. That's a job that you can get. So this is definitely a career path. All right, enough yapping. Time again, more yapping. Sorry. All right, now to a quick explanation on how Altium works, so that once we start jumping in, you know what's going on. There's two documents. There's a schematic document, and there's the actual PCB. So the way all Altium needs are two things: what the components look like, so the footprint, and how the components are connected together. So the connections, right? The nets, right? So on your schematic document, well, you'll actually be drawing out the schematic. So probably what you've seen in class, right? It'll hold the schematic, it'll hold all the connections, and that'll update the PCB document, and Altium will then know how everything is connected. To supplement these two main documents, there's these two libraries. There's a schematic library that holds all the symbols for the schematic, and there's a PCB library that holds all the footprints. You'll see once I start actually putting it together. Yeah. Okay. So don't worry about that. We'll get into it later. Now, how does the actual piece, what does the workflow look like? And basically, this is what today's workshop is going to look like, as well as next week's workshop. Today, we're going to look at the schematic for the circuit. We're going to choose the components, and we're going to figure out the footprints. Or ideally, yeah, figure out the footprints. Next week, we'll actually be laying out the components on the PCB board, and then I'll show you guys how to get it manufactured. So this is going to be it's going to be a two-part workshop, but by the end of it, ideally, we'll be going through the entire workshop. Cool. All right. Okay. Last slide, I swear. Last slide. This is the circuit we're making today. Who went to the oscilloscope workshop 2 weeks ago, 3 weeks ago? You two did. Okay. So for those of you that didn't go, they built this circuit on a breadboard. All you do is you press the button and you turn the knob and it makes a different sound. I don't know if you guys can hear that. But like, if you look at it, it's very messy. And if I tilted it upside down, I imagine half the wires would fall out. That's how we're going to build it on a PCB. See if that happens. So that's what the schematic looks like. You know how to memorize that. I'll be building it later. But it uses a lot of components. All right. Demo time. So if you haven't already, let's open Altium and we'll get started. Oh my gosh. Well, now you're gonna learn by doing it now.
I can't.
Okay. Oh, then just sit here, I guess. You won't learn at all then. How about that? No, there's no doing, there's no learning. Okay, anyway. Um, I'll give everyone like a few minutes to open up Altium. Um, let's see. Jesus. All right. So if this is your first time opening Altium and you've got the student license, the first step is actually going and turning the license on, if that makes sense. So click on the top right there, very top right, not the X button, and hit licenses. Licenses will pop up this panel here, and it'll show you the different licenses you have available to you. What you're looking for is to enable the one that's called Altium Designer Professional. So let me like release it for now. So it's probably looking like for you, ignore all the red ones. It probably looks like this for you. What you're going to do is find Altium Designer Professional and hit use license. And what that'll do is it'll say that your computer is now taking up a seat on that license. So that also means is you can actually use Altium on multiple computers. You just have to remember to release the license when you're done. So on the other computer, you can enable a license. That also means you can kind of share licenses too, as long as you're releasing it properly. So the way they do it in industry is they'll buy like 16 licenses, and then they'll have like a team of like 50, but they'll just say, if you're working on it, use a license, but when you're done, get off the license. So shoot.
At my internship, my mentor was telling me that I worked at Disney. He was telling me they used to implement it a different way, which was even worse. It would run an instance. I don't know how they set this up. It would run an instance on all 50 people's computers, but then if you tried to enact a change, it would timeshare you with 6 licenses. So it would lag basically until one was available to implement it, then it would kick you off again.
You had a question? Are you just stuck? That's a
They endlessly complain about one.
Yeah, you don't have the license.
Yeah.
You get it's already in the software.
Did you get an email? Did you do this where you went into the student lab? Student lab. Did you do this process that I put on the Discord? You hit enroll for free and then you use your students. It's so general. Okay, then you won't. It takes like a day to get the license, so you won't be able to participate today. But you can watch. Shoot.
Oh, that was it.
Just have to say that again. I got a free license. I use license.
You got it? Okay. That's good. Okay, then try it out right now. Do this right now. I put an announcement, guys. All right. Hit enroll for free. Put your Cal Poly email. Put Cal Poly Pomona. Hit start verification. You're gonna have to log into CPP. You can follow a form, guys. Right? Do that. Okay. All right. Who has a license? I want to make okay. And you guys were able to use license?
It only takes like 10 minutes because it takes a bit for them to send you the email.
Yeah.
But it's like 5 minutes.
Okay, that's good then. All right. So those of you who didn't do that, do that. Cool. All right. I'll move on for the sake of the recording and sake of people that have the license. Cool. All right. All right. Let's see. So what you'll see on the left there should just say Project Group 1. You guys see that on the left panel? If you don't have that panel, and if you're ever missing a panel, you can go to the bottom right here, the button that says Panels, and you can open up the panel that you need. So whenever you're like, Ryan, you're on a screen that I haven't seen before, and you're missing a panel, go to here, you can find your panels. So we're on the project panel here, and you can, well, now create your project. Go ahead and right click on that project group, and hit add new project. So now we're creating the buzzer project. So let's see. Local projects here. The reason you're seeing this cloud is because I'm on a different workspace. So, all right. So local projects, and you can name it whatever you want. Let's name it a buzzer circuit. Sure. Um, Everything should be fine. You can check the folder to see if it's saved in a folder that you like, if you guys have different drives. And do not click constraint management. Leave that unchecked. I'll explain it next week. But we do not click constraint management. But name it buzzer circuit and go ahead and create your project. All right. Cool. So everyone should have a folder on the side here. Sorry, I can't really like zoom in there. If I can do it. Can I zoom in? Not really. So now you have your project, right? Now we got to make those 4 documents that I talked about earlier, right? So go ahead and right click on the project and hit add new to project. What we're going to want is the schematic, the PCB, the schematic library, and the PCB library. So go ahead and just click on every single one of those. So right click, it's opened up the schematic. Right click again, add new to project, PCB. You got to give it a second sometimes. Right click, add new to project, schematic library. And then it's going to pop this up. So you got to go back to projects here. There's the panel on the bottom. And then right click, PCB library. So those are the 4 documents that you need, like the basic documents you need to make a PCB. So there's a tab at the bottom. So yeah, the Altium likes putting their tabs at the bottom here. You'll see there's a lot of tabs at the bottom here, as well as tabs at the bottom. So if you're lost, search there. There's some weird. You got some like how they do it to lost it's kind of software. Yeah. You try up to or maybe it's Who's able to make the 4 documents? Schematic, PCB, schematic library, and PCB library. That's it. I've got it over here. So schematic, PCB, schematic library, library. All right. So you can also look through the different tabs. You can see your schematic is completely blank. You see your PCB is also completely blank. You can see your schematic library is blank and everything's blank. All right. I'll go to 135.
Can you really call it a long library? There's no file in it.
Yeah, a burned down library is still a library.
Is it? You got add the information. You go to figure. I'll be on the right.
Say again? Yes. Yeah, and then for your email, make sure you put up like that's right. Basically, they need to verify that you go to the school. All right. Tier 3 arrived just in time as well. All right. Sorry?
You can Google that. We're just like
I don't
Ryan, your shoes untied.
you got me.
No, I'm not even memeing though.
Yeah, I know it's my shoes suck. All right, let's move on. All right. The first step is that we're gonna want to build our schematic, right? but we actually don't have any parts to make the schematic. So let's actually start there. Go to your schematic. So let's go to your schematic library. And what you should get is a screen that looks something like this. There's a whole blank area there. And this left side are all the different components in your library. You have nothing. Well, you have one, and it's like a placeholder called component one. So let's start by making our first component. We go back to our circuit here. Let's start with the resistor, right? The good old-fashioned resistor. So go ahead and at the bottom, click the word add, and just type in the name of the component. Let's just do resistor, just for simplicity's sake. All right, we've made a component, resistor. I'm going to drag these over. Oh my gosh. All right, drag these over and drag this over. All right. Now, let's see. The first thing that a resistor, okay, so who doesn't know what a resistor looks like? Looks like this, right? It's like a wavy shape and two ends, right? So to start, let's start with those two ends, those two terminals or pins. So go to place and then hit pin. Now, what you should see is a thing moving around that has number 1 on it or 0 on it. Is it 1 or 0? Zero? All right. The reason it says 38 for me is because I've done this 38 times. All right. This is your pin. This is going to be one end of your resistor. So if you actually were to place it down, and if you hit Control and scroll wheel, you can zoom in. So if you look at it, can you guys see that? There's 4 dots at the end there. That is actually where it's going to connect to the wire. So maybe I draw 4 dots here and 4 dots. Cool. So that means those have to be pointing on the outside of the component. So if we go ahead and place another pin, so place pin, and now we want to place one on the other side, but our cursor is where the dots are, so we have to rotate it. You can rotate it by pressing the space bar. And let's place it here. And if you zoom in, you can confirm those 3 dots, those 4 dots are on the end there. And finally, to finish everything off, go ahead and click on your pins. Actually, you guys are fine. I need to rename them 0 and 1. Look, this is my punishment for doing this too many times, right? And feel free to also just hide the name. So there's a little like eye icon right there. You can hide the name, makes it a little cleaner. So now we have our 2 pins. Now, I will start by saying, technically, we don't need to do anything else. This is it. But if you imagine your schematic is made of a bunch of just empty gaps, it's going to be hard to read. So we need to make a symbol that's going to help us know what component this is. So let's try to draw one. So now that's your artistic drawing skills. Go ahead and go to place on the top there and hit line. And now what you can start to do is draw a blue line. That's your symbol. So if you hit the space bar, instead of rotating it, it's going to change how that line behaves. So you can see how it gets altered like that. Let's try to make a diagonal line like that, like that, like that, and like that. And hit escape. Or maybe that's, if you hit escape, it set. Maybe that's a bit weird. I'm not dragging, I'm just clicking. So place the line, click on the top end, and click where you want it to end, like that.
I'd say have the first and last line segment only be half as long and its middle.
Is that your, so let's see. Like this. Okay. Now I'll leave like this. So there's a bit of artistic flexibility in this. But the main thing is that you understand exactly what this component is, right? It's a resistor.
Why are super basic things like resistors not just included?
Um, they don't assume anything. Like remember that component library was completely blank. So if you actually your circuit doesn't need resistors, I'm not going to give you. That's it. That's like a difference between this and KiCad. KiCad has downloaded an entire parts library, but this is us making custom parts.
Is there like a standard parts library you can download for this? If you
Yes. Yeah, but it's a bit of a process.
Oh, okay.
I've never found the need to, if that makes sense.
Like, you know, like, yeah, I think important, right?
Yeah.
I think what I mean with like behavioral properties of stuff like element, like how do you include that in your component?
Behavioral elements, like mean like simulation.
They have that like if someone picks on your, that's why I ask you schematic folder, they pick on your component, because they're a way for them to easily reference within the environment and see, oh, there's this data. This component.
Yes. You can import the parts from the manufacturer. Like I said, you can download parts library. Yes. Right now, we're just making custom parts. All right. Who was able to build a resistor? Okay, good majority. I think one last thing is we're gonna now have to put a designator for our resistor. Now, if you guys seen PCBs before, often you'll see them marked as like R, like R1 or R2 or R209, right? So we can actually have that designator by putting R and then a question mark right there on the top. So when Altium puts all these components together, they can automatically populate the question marks with the numbers. So yeah, actually that pin shouldn't be. I'll just call it pin 2. It might be probably easier. All right, pin 1 and pin 2. R question mark here, and you have that drawn like that, you're good. Oh, on the side here, my bad. There should have been a properties panel that popped up when you open this, but if you don't see that properties panel, go to the bottom here, panels button, properties, right? Whenever you're missing one of these panels, just look for the name and see if you can pop it open on panels. So panels, property. And you can see there's a bunch of different properties too, especially there's this for you, manufacturer part search. You can actually search for parts here. So very handy for getting those data sheets. Yes. On the bottom here, are you on the schematic library tab here?
Yeah.
What? You're looking at the property of the line right now, so click on it, and then now there. So that's actually a very good point. You can actually search for the properties for any different component or even part of this component. So if I double clicked on the pin there, it actually pops up the properties for the pin. If I double clicked on the line, I could actually pull up the properties of the line. I can even make it a different color. I don't want to. You can make it a different color. But if you click out of it, it takes you to properties of the entire component. Okay, cool. All right. We're going to build another. We actually have a lot of components to build, so we're going to have to get used to this flow. All right, go ahead and we're going to make our next component. I think in this case, it's going to be, let's make a capacitor. So click add and type in capacitor. I think I spelled that right. So now we have a new component on our schematic library called capacitor. So first step is, of course, place down our pins. So there's pin 1 and pin 2. This might be harder if you're using a touchpad, but it is doable with a touchpad. And then name them pin 1, and am I talking? Okay, I am talking. All right. And pin 2. You can go ahead and hide the names so they don't get in the way. And those are our pins. Now, remember, technically, we can leave it like this, But if you try to read the schematic in the future, you're not gonna like yourself. It's like not putting comments in your code, right? So let's place a line. Let's draw a capacitor. Now, if you guys know what a capacitor looks like, is two parallel plates. Something like that. You can kind of like mess around with the spacing to make it nicer if you want. It doesn't have to be centered like that. Um, let's see. Another thing you can do is you can actually change the length of these pins if you think they're too long. So if you double click on the pin and you go to here, you can actually change the length to be different. You can make it like 100 mil instead. Maybe 100 mil. Again, decorative changes. These are all decorative changes. Main thing is just you have these. You have the pins. Everything else is like, should be what. And think last thing is the designator. Instead of R, this capacitor is going to be C, maybe C1 or C5 or C250, right? C question mark is the designator. And then I'll give you guys a moment. You can adjust it as you will. I'm just left clicking here. Called the capacitor, pin 1, pin 2, and designator C question. I'll give you all a moment. Raise your hand if you have any, if you're stuck or have any questions. Yes. Wait, raise your hand to what? Any like questions? Oh no, if you have it, you're good. Okay, yeah. All right, who's got it made? Okay, I'll give you all another moment. I'll wait till 148. Okay, 148. Okay. Next, we got to make so many components on this thing, right? Uh, let's see. We made a resistor. We made a capacitor. Let's make the potentiometer. If you guys look at that symbol, it's exactly the same as a resistor, except it's got a curve. So let's go to Altium, add a new component, call it potentiometer or POTS, variable resistors. And one trick you could do is you could copy paste. So maybe it'd make our lives a bit easier if we were to go to our resistor, highlighted the whole thing, Control C, Control V. Wow, look at that. Place that down like that. And all we got to add is an arrow. It's like a line going through, maybe not like that. It's a good way to do this. Place line, maybe like that. I think that should be good. Is there an arrow as well? There is a pointy bit. So maybe place line, add a little pointy bit there. Again, purely artistic, was it, liberties right here. And I think, I don't know the potentiometer reference this. Yeah. Arrow. Okay. I'm going on to Wikipedia, and there's actually a whole Wikipedia page for reference designators. So they actually tell you what the letters they use that are standardized for all those things. Do you see for capacitor? And I'm looking at it, and I see RV is for variable resistors, or varistor, I think they call it. So why don't we do that? RV question mark. RV question. And that RV is going to be put in like RV1. R. Cool. Copying pasting it makes it a little bit easier. Everything should be intact. Pins names are 1 and 2. The arrow. All right. Who still needs more time? Oh, perfect. All right. Move on to the next component. Let's see. We can make our buzzer. Now, if you Google buzzer schematic, if you looked up what a buzzer actually looks like, it seems they're a fan of like this shape, this like box with like a little speaker coming at it. Let's see if we can try to draw that on our board. Now, if you look at the buzzer, actually, let me pull up what buzzer we're using. We're using this kind of buzzer. Have you guys seen these before? They're like 2 pins, the 2 terminals, right? And it's like a little buzzing thing. All right. So if we were to make our new component, call it a buzzer. Yes, I know this is very brain numbing, but like we gotta get through this, guys. All right. Place your pin. And this time we're gonna place them vertically like this. So that'll be pin 1 and pin 2. Okay. And actually, it might be useful for us to name them what they're supposed to be. So one of them is going to be ground, and the other one is going to be V plus. So power in, power out, right? And this time, let's place a rectangle. Wow. Something like that. Sure. Dang, it covers the.
Back.
Let's see. View. You think rectangle, right click, place, tools, view, border. What about these?
Oh, we can just move the fill.
That too. Damn. That makes like a sad component, but sure. Place rectangle. And if you guys look at the actual menu label, you'll see the letter P is underlined. That means if you press the letter P, it'll automatically pop up. So if you get in the habit of using those letters, you can actually start to do things really quickly just by having those kind of like shortcuts. So yeah, let's see, maybe a bit scuffed. Man, why is it on the top? That's not normal. Okay. I can make it transparent. Oh. Okay, yeah, that works. All right. Hey, give it up. He's got it. All right. And maybe we'll put a polygon that looks like okay. Sure. I've never done a polygon before. That is very horrendous.
Smallest round.
Yeah, that's what I'm doing. Oh, okay, that's pretty good actually. Okay. So if you don't know what I did, I hit polygon and it lets you draw like a custom polygon. There's our buzzer right there. And it's really nice to have those pins, B plus and brown, because for a resistor, And for a capacitor, it really didn't matter what the whether they're flipped around. But for the buzzer, it actually does matter where it's flipped around. It doesn't it's what they call it's polarized, right? It's not a non-polarized component like these. So it's good to have these labeled. Actually, come to think of it, I think that was supposed to be.
A lot of capacitors are polarized.
Yeah. Oh yeah, they are. But not the one we're using. We're using a ceramic one, so it will not be polarized this time. But for if you do have it, it's good to label them pluses and minuses. Who still needs time? Okay. Um, if you go to place, and then you can hit polygon. Hopefully, we're getting used to the UI bit. And I think I forgot. Okay, designator. If we go to our designator, was it Wikipedia page? If you look at Buzz, okay, they're using LS or SPK. Sure, we'll do yeah, SPK, like speaker question mark. Okay. SPK. Well, a bit of fun with it. You think of it that pod has 3 terminals.
Are you using all 3 terminals or only just the 2?
No, but our footprint's gonna. Actually, I think it's yeah. Yes, it's or we're gonna post it on our YouTube channel, put a link. So Hmm? Yeah. It's this will be recorded. I'm recording it right now. Actually. Thanks for coming. Were you able to sign in? Okay.
I'll just catch up.
Yeah.
Let's do it.
Yeah, we'll do it next week. Come back next week. Yes. Yes. Because we have the dots here on the outside, because that's where the wire is going to connect to the pin. If you have it flipped around, it'll still be fine, but it'll be really awkward because the wire is not going to connect to here. It's going to connect to here. So it's like when you have the trace, it's going to look like this. This is going to look a bit like silly, right? So it's like it's better to have the dots on the outside so that the trace connects to here. At least on the schematic. Again, it's decorative, right? But that's good. It's good for when we're using them. Yes. Oh, this is how you do with because they're going to see that because you're talking about we're keep adding new components, right? Or maybe new ones. Because these are going to be considered one unit. So if we were to place them onto the same component, well, what happens is when we place it, it's going to all be placed at the same time. We're going to want to be able to rearrange these parts. These aren't separate libraries, these are separate parts. This is all in a single library, the schematic library. No, we don't want to do that. Because what'll happen is those will be fixed like that. So whenever you move one, it's going to move the other. And also it means they're only going to have one designator. It means there's reasons why we're ranking separate parts. Does that answer? This is practice. Yeah, industry. This is standard practice. Especially when you want to place multiple parts. So say we had the resistor and the buzzer on the same page, and we want to place 2 resistors, we would actually be unable to, because if we place this part, it would come with another buzzer. Yeah, exactly. And also, each one of these parts are also going to be assigned their own footprint too. So having multiple parts on a single page is going to not. This is just how it's done. It's like we're making different. Every part gets its own page, right? Okay. Putting 2 parts on the same page will just make a single part that's made of 2 parts. Yeah. Okay. What are we on now? I think we're on something. Let's make a switch. All right, we're almost done. I think we're halfway through. Switch. We're gonna make a switch. So I made a component called switch. And you're gonna have to place two pins. There's gonna be one pin here, one pin here,
Ryan, do you ever
one.
develop a geometry that we just name it?
Huh? Yeah, I already made.
Oh, wait.
What are you thinking of? Okay. All right. We're gonna make our two pins and a switch. If you look on that schematic, looks something like that. Looks something like this. Pin, and another pin, and then there's this floating bar, kind of like a button that you're pressing down, right? To connect the two terminals. So we can draw something like that. I'm gonna say 6, 7.
Yeah. Not on the.
Oh yeah, because if you guys place the components by now, you're probably on pin 6, 7. Yeah. If you've been following along, you'll now see 6, 7. So, thank you. All right, and we're doing SW question mark because it's a switch one. Are we getting the hang of this? Is this making sense to people, this process? It's getting faster and faster. Switch, two pins, draw a symbol to make it all work. Correct. It does not matter. Yeah, because this is going on the schematic. Everything is, you can think of everything as decorative. The only actual thing that matters are the pins. Because the pins are what we're using to connect the components together. That's all, that's what Altium needs. Everything else is for our benefit or for the benefit of your peers when they're looking at your schematic to know what's going on. It's like commenting your code, right? So you know what's going on. It's like, it's good to be able to like troubleshoot errors, get the pins right, all that good stuff. All right. Switch. Cool. Who still needs time? Okay. Next component is a I want to save the 5-5 timer for last. Let's do the jack. The jack. So if you guys, well, I'm saying guys, but let me see. I think the one thing that's a really common mistake to make when you're making these circuits is forget how you're powering the thing, right? Because there's no component on here that if you were to go over just the schematic, you would bake 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 components, right? Maybe 6 components. But what you're forgetting is you need another component to supply the voltage. That's what this power jack is for. So if I were to open it, if it lets me, it looks something like this. Right? And the idea is once you have your 9-volt battery, 9-volt battery clip, you'll be able to clip it on using one of these. And you'll be able to just plug it in. So it's really useful. So we're able to just power it. Cool.
Why does it have 3 pins?
Because it's actually designed for more than what we're using it for. Because you know how like audio is using these same jacks. So there's a third pin that actually actuates when you plug it in. So it basically gives the circuit a notification that it's plugged in, if that makes sense. Well, for what we're doing, we don't really care about that. We just want power, right? So with this idea in mind, we're going to be installing one of these onto the board. And we can probably figure out a cool way to draw it. Let's see. Maybe if we just drew a box and we had a circle at the end, that should be good enough. 3 pins like that. Call out the jack, so J1. I think that's fine. All right, let's go ahead and build that. So we can start by placing, maybe let's place a rectangle like that. And we can place this time a circle, full circle. Maybe just put one right there. Maybe do it like this. It's a circle at the end, and we have our pins. There's actually going to be 3 pins on here. So, got to rotate them. 1, 2, and 3. Call that pin 1.
A6.
Okay. You can name one pin, pin 67. Like this. If you build those microcontrollers, you'll get a pin. We're dating this recording now. Everyone's watching the recording, like they made a 670. That's crazy. Yeah, this is probably good enough. J question mark.
Name the fifth label, power ground.
So that's a great point. And often when we're looking for the labels, we can just find them on the circuit schematic. They also label it once. Yeah. So having at least the designators the same makes us how we know what's going on. If that makes sense. But because I don't remember, I think we have to short 1 and 2 together, and that's power, and then 3 is common, or it's the other. I have to make it up. But okay, that's our power jack. Finally, we have the last chip, which is the thing that's controlling everything, the 555 timer. The 555 timer is a 6-pin chip that, well, has 6 pins. And it's the oscillating circuit that's actually firing the entire thing. So if you type in, let's call it LM55555. And now we need to build the LM555. So I go here to DigiKey. As you know, we're searching these parts up on DigiKey, right? And they actually tell us, oh, it's an 8-pin chip, my bad. They actually tell us, well, they give us where you're going to buy it, right? But they also give you something called a data sheet. Especially if you're doing circuit design or PCB design, you're going to be living in these data sheets pretty much all the time. The data sheets are what tell you how everything works, what every pin does, as well as like all the different tolerances and maximums and all that good stuff. So Texas Instruments is great. They make really nice data sheets. There's other companies that make really crappy data sheets. So if we were to go to the pin configuration, or rather these pin functions here, we actually have the names for each of these pins. So let me draw it here. Can you all see this? Okay. So pin 1 is actual. I mean, why are we doing this? Do we already have a schematic here? All right. So this pin right here will be pin 8 for VCC. VCC. All right. You don't have to write this down. I'm going to do it when you guys have it. We have a Q. That's pin 3. We have DIS. That's pin 7. We have THR. That's pin 6. We have ground, which is pin 1, G and D. We have R. That's R. That's pin 4. CV is 5. And TR is 2. Now, what you'll notice on the schematic is that these pins are completely, like, they're not organized, right? On the actual component, they are numbered 1, 2, 3, 4, 5, 6, 7, 8. So the important thing is that we can actually determine what the part looks like on the schematic. It doesn't matter. Because like I said before, the pins are the only thing that matter. So if we were to draw our 555 timer, we just place a rectangle. We can just start placing pins where we want them to go. So let's start with this pin. And yeah, notice how I'm circling it. It's like center on my cursor, but I'm orienting it like this because my cursor is where the output is going. So I've got one pin here, one pin here, and one pin here. Here, here, and here. One at the bottom and one at the top. And if we were to name them, maybe this top one is what? Pin 8, and the name is VCC. So the designator of the pin is what's determining the pin number. That's very important to have correct. Because if you have the wrong pin number, what's going to happen is when you build the footprint, it's going to be misaligned. And then you're going to have the wrong pin, and then now your circuit's actually not going to work. So we've got this one is going to be pin 3. The name is Q. We have pin 7, and the Name is DIS. We have pin 6. The name is THR. Okay. Pin 5 is pin 1. The name is GND. This is pin 4. The name is R. Pin 5, CV. This is pin 2, IR. That lines up. This. Yeah, trigger, threshold. These are like shorthand, these are shorthand names for the actual MIPS. I think it's like reset, trigger, threshold. It's not IR, it's TR then, is it? Yeah, that's TR. So trigger, TR. And the designator for these sort of chips are U. So U question mark here. So for basically all IC chips, you're going to see like a U reference designator. So it'd be like U5, U10, but it can be at different kinds of chips. But the main idea is that if it is a chip, it will be a U question mark designator. Of course, the rest of it is decorational. Was it decorative? So maybe we can make these a bit smaller to make this chip not look like a porcupine.
Can you select multiple pins at once?
Maybe, but I don't know if it'll do this. Try it. Oh yeah, okay, there we go. So if I do 200, no, it's a bit weird. If you guys can figure it out, then try it out and it should work. That's our profit back time. Thanks for coming. Cool. Oh, it's from here. DigiKey LM555. They have the data sheet. Yes. Oh, yeah. There's a bunch of different kinds of 555s. Actually, if you were to look up LM555, they have a lot of different kinds of 555. And you'll notice that one of the main differences is that they're using different packages. So like this one's an SOIC, that one's an SSOP, or the SSOP, that one's SOIC. But the one we're using is a basic through-hole version. Yes.
Would it be wise if the chip could be swapped out if it breaks and to prevent infections? Do you use one of those like IC sockets?
Yeah.
One of the components?
That would be very wise. What's nice though is that the footprint will also look exactly the same, so you don't actually have to put that in. But if you were building it and you had one of those handy, you could swap them ideally. Yeah, but very good point. Actually, it's very recommended for things that are very high risk, things like microcontrollers. Very nice to just slot it into like a header, or like if you've seen those Arduinos, you have those like for the chips as well. Yeah.
Want to change multiple pins at once, you can hold down shift and then click on multiple pins and then you can change.
It works. You're able to do it. Nice. All right. So that's new technology. Yeah, you can change multiple pins at the same time.
Right.
Good work. Yeah.
So if you wanted to do a chip socket though, because if I remember the chip sockets are surface mount, if the chip is through hole, so how would you distinguish that from the PCB?
Oh, if it is a surface mount, you're gonna have to then make a component that just says that chassis and make a footprint for that. Actually, that'll probably be I think that's best practice is to make the actual component. And then if you go into the data sheet for that socket, they'll tell you the recommended PCB layout. So if it is a surface mount socket, which I find very weird, I feel like a lot of the sockets are through-hole. But if they are surface mount, yeah, you can put the right filter. Yeah. All right. Who still needs time? Are you good? All right. We're done. We're not done yet. But we finished making all of the schematic symbols, right? Give yourselves a round of applause. All right. Now it's time for the fun part, putting them onto the schematic. So now let's before you go, hit Control S to save the schematic library. Just name it. You can save it as the default name, or rename it. But now you have a finished schematic library. So now let's pivot to the schematic. All right. Now what we're going to want to do is place the components down, right? So if we right click the board here, or not really, no. You know how before it was placed? Now if we go to the place here, it's a different menu. We can hit place part. And on the left side, or sorry, on the right side, it should pop up a panel telling us the parts. Now, it probably doesn't look like this for you guys. What you probably see is this bottom section where it says the name of your schematic library 1. So if you click on that, those are all the parts you made. Oh, we made earlier. So again, we want to open the component. We also, if you want to open this tab, go to panels at the bottom here and hit components. And that'll pop up this tab. And what you're looking for is the library called schematic library 1, or whatever you name that file. If you don't see this, make sure when you were in your schematic library that you hit Control S to save. I know I did it really quickly. But when you hit Control S, it should pop up a file to save. Actually, for now, why don't we do that too with this schematic? Hit Control S, and it'll pop up a menu like that. And you don't have to rename it. You can just hit it, save, and I'll save that document. Yes. Is there all? You might also have to do that as well. There's a. Does that say refresh on it? It does say refresh. Yeah. Feel free to hit that as well if it doesn't pop up, and that'll also save your schematic, or that'll pop up your schematic library. All right. Anyone need help finding their parts that they spent so long on? Is that a raised hand? Oh, so it's helpful. No. And you should pick schematic. You got the remove stuff. Go back to the
Oh, supposed to have a other version of the duo. Open you.
Backwards.
Yeah, kind of like what he has, but what? Small. But the characters.
Anyone else need help finding their parts? If you recall, it's panels for components, and you're looking for not simulation generic components, but your schematic library, the one you built, right? And if you don't see that, hit refresh, and it'll refresh. Cool. Who still needs help? Anyone need help? Yeah.
Put it back together. My goal is that I think it's the impact of putting it, make it each protrude. The things the batteries are so strong, it's so solid that I don't think it's that way. It would be like maybe I think it's relatively small as a
Yeah. Yeah, you can essentially help with your battery by putting on.
Yes. All right, let's move on.
All right. Let's play some components down. If we look at our circuit, what's a good place to start? Let's put let's put the 555 timer down. Why not? So if we go ahead and drag that component in, it'll give it a sec. It'll pop up like this. And you'll see what we gave it, the U question mark designator, and it even popped up the name as well. All right. We can honestly just drag everything into it. So there's our power jack there, maybe power it here. There's our buzzer right there. There's a switch that should be connected to our power jack. We have a resistor somewhere here. We have our capacitor somewhere here as well as a potentiometer here. So that's the whole gang's there, right? I think that's everything. Yeah.
You. Make it.
Go ahead and see which solution. So if we can put us right.
Yeah, if I were making it, that it would be this group, which I would want.
So they just.
It's also like. It's nice poppers, like you see with the
Regular.
I just
my.
No, I like the triangle ground, but not the line one. I like this one, which in Tech is called S ground. You're supposed to, by IEEE standards, only use that. Really for like a small signal ground. It's not an actual ground, but I don't care. It was better than the active ground. You guys have something my house was stopping. Like be a virtual ground or like I think
I just need to hang tight then. Or delete that schematic, like remove it from your project and make a new one. So if you right click it, there's a remove from project button. You can always remove a sheet from your project. All right. Let's connect it together. So, well, what are we missing right now? We're missing a wire, right? So if we go to place and then wire, it'll allow us to now place the wire to connect everything together. So I know on the top here, well, what's the best way to do this? Look at our sheet. We know that our capacitor, well, okay, let's actually start with the ground. We need a ground node in order to connect everything to ground, right? So what we can do is actually, before we place a wire, we place a power port. And what it looks like, well, right now it says VCC, but we can double click on this, or, properties, right? And change the style to be a power ground. And we can name it G and D caps. Thanks for coming in. Oh, that's great. All right. All right. So now we've made our port right here at the bottom that says ground. Now, the nice thing about these nets is that anything we connect to this ground port will all be connected together, right? So we'll place one ground here. And it should have made a connection. We can copy and paste that ground to go onto the buzzer as well as our capacitor. And remember, the space bar still works when you're placing these down. So you can always rotate these around. Okay, what else we got? So the capacitor, you see that net is connected to THR and TR. So let's try to do that. Place a wire capacitor goes to THR and TR. Now, it is a bit of a weird angle, so you can go ahead and draw lines like that. Maybe that's kind of weird, so draw it like that.
Else you got to flip around.
Where?
Back.
That's right. I was gonna save that for later because I actually need to look up what which one is ground and which one's power. Actually, can we bring that up? All right. Now, after this capacitor, we need the potentiometer and then the resistor in series. So we need the potentiometer here, and then the resistor. So notice that changing the symbols actually helps a lot when building your schematics. If you look at mine are very large, so it gets a bit clunky. So being able to design them properly is a good way to go about it. Now, but look up there. Yes. Okay. Save it for later. Actually, let me just look this up real quickly. Power jack. It's brought it up. Just form here. Yeah. So pin 2 and 3 are pin 2 is ground, pin 1 is power. Okay. So pin 2 is what did I just say? Pin 1 is power, pin 2 is ground. Pin 3 can be left floating. I said it out loud and I forgot it. Pin 1 is power. Okay. So pin 1 should be connected to our switch, and the switch will be connected to that resistor. Pin 2 is connected to ground. So actually, that's bad. Don't do that. Thanks for coming. Right. What else are we missing? The power here should be connected to power here as well. I don't know why it's doing these weird non-90 90-degree angle connections, but it's there we go. What else we got? Pin 7 is connected to the middle of that voltage divider. So place a wire from here to here. Why is it doing it like that? That's so weird. And Q is connected to the buzzer. I think R is connected also to power. Place wire. R is also connected to power. What the heck? Place wire. Okay. It's a bit messy. Maybe move it around a bit and make it better. All right. Actually important to note that this wire is not making a junction because those two are different lines. Yeah, those two are different lines. So make sure there's no dot there. But that's the circuit in a nutshell. Now, what's what you
Pin
can
5 connect anything?
Nah, pin 5 is a no connect. If you look on the schematic, pin 5 is a no connect. Oh, on here, you notice how the dots are connecting the two lines, right? But there's no dot, shouldn't be. Yeah, there's no dot there. Oh, you're gonna have to delete the wire and remake the wire.
Why do you like not have it either?
Don't have the wires intersect is basically all you can really do. So it actually comes into actually building the schematic components, giving yourself enough space. I know for that jack, we kind of did a little bit of like off the cuff, so it wasn't too on point. Yeah, not very professional. All right. One nice thing that we would want to do to prevent any errors is to mark the pins that were not connected. So, for example, this pin 5 is not going to be connected, and that pin 3 is not going to be connected. Now, Altium will actually tell you that those are not connected, and they'll mark them as errors. If you want to tell them that there's no error, you can put a generic no ERC or electrical rules check. So you can actually mark that on those pins. They won't ignore those errors. Like they'll ignore those off pins, or the disconnected pins, floating pins, that sort of thing. Let's see. I think then you spend the rest of today making a couple footnotes. Move on to next week, part 2. Yeah. Who still needs a bit of time? That's fun. A lot of people. Yeah. Oh yeah. So you'll notice on this 5 timer there's no pin connection, and that pin 3 of the jack is also not connected. So on Altium, they'll actually mark them as an error because they're like, you forgot to connect it, right? What you can do is place, and you place a directive called a generic no engineering electrical rules check. What it does is just says, it's fine. Don't worry about it, right?
Speaker, how do you like the top one for me that
Is it like, so let me see if let me try. All right. So if I place a wire and you got it like this, you should be able to just place it above and it won't make a connection automatically. It's only when you move the wire, I think, then they'll think that you're trying to make an electrical connection. No, at least on my end, it's fine.
And then if you move the wire with your cursor starting near the line,
Like here, or if I click on the part here. Oh, I see what's happening. I'm having it intersect my part. Like that's not a wire, that's a pin. So if you have it overlaid on that, it's gonna fail. It's not that. Another way you could try going about it is moving these along like that instead. Um, Maybe that'll make it easier. That can go here, that can go here, maybe that can go here. There you go. Okay, then there's no intersection at all. So get creative with your placements. This is actually going to come a lot. It's going to be a lot in. This is going to come a lot into play when you're doing the routing because there's a lot of creative routing decisions that you can take. But that should. That's. There's a lot of these. Maybe moving this here, moving that down there. I'm not sure how to go about fixing that one. Yeah. Yeah, it means it's not. There's nothing touching it. So we could just leave it floating, but when Altium like scans through it, they'll just like give us a warning, like, "Hey, you forgot about this pin." So when we place the X down, I think I mentioned it earlier. Place directives, no engineering rules check. That X just tells Altium it's fine. There's no worry. That's what ERC stands for, electrical rules check. I think you can even run an electrical rules check somewhere. Yeah. Any other questions? I love answering questions. Yes. Oh. There's actually police limits. So yeah, I have to.
More or less 6, 7.
You can, well, yeah, I still.
Yes, of course, it's a 74.
Low power.
Click on the, and click on the thing. Maybe now it's.
This is kind of a type.
It's like that. Yeah, there's still names to the dots. Here's something. Or. It belongs. It's placed on the dots, on the dots.
So I just called 6 step and not even called 6 7 anything else. It was just 6.
That's actually cool.
So actually, that's a very good thing to bring up. Say you made a mistake on your symbol, right? Say like it's messed up. What we can do is, even though we placed the part, we can still go back and fix it. So say I want to like redo the diagram on this jack, right? I could go back to my schematic library. You guys don't have to do this, but I'm showing you for your own information. But say I wanted to like adjust like the symbol, it looks kind of weird, so I adjust it. What you can do is after you've adjusted it, save it with Control S, and if you right click on the empty space, there's a selection that says Update Schematic Sheets. So when you hit that, every schematic that has that part gets updated with the new model. So as you can see here, updated one component in one schematic document. So if we go back to our schematic, it's shorter. There's a little change. So if you make mistakes to the symbol that you discovered, you can still change them. And you can update your schematic sheet with the new symbol. Does that make sense? Yeah. So when you make the change on here, all you have to do is just click this. Right click, update schematic sheets. Single button. Well, you have to right click and then so it's 2 buttons really. But you click it and I don't know why it updated it a second time. It's kind of weird. Oh, and then now you got to save it on this end. Hit Control S, and now it's here. Who's still working on the schematic? Two people? You help?
We should buy 67, 67. Well, no, he found one more first. It's listed as 6 7, and it's like a PC charger.
You know what the
Four by four, but I have the files to be
yeah,
updated.
Yeah, that's the job. I know how to do it.
Well, you can do what I just did. So your schematic library updated on schematic library.
Did you find a part that's called 6 7?
Yeah.
Take Control S.
So much it costs.
Or like, look at it. The less to say.
Sadly, it isn't 260. That's just short.
Exactly.
You know, it's the best.
Oh,
Classic.
Yeah, but you happy if I'm cheating on it. It's coming.
You think the place? Oh, there it is. Do you think sometimes you're going to place them backwards so that it's not text?
What I mean, the thing is, just in that place, the company, it's not probably what's on it.
Wait, where does it say?
Pictures.
Oh, I did not know that. That's probably so funny.
Go to your two forward.
Oh, I see. Interesting. That wire is.
You do it automatically. Say
Yeah.
save like that. It's also so slow. Like. Firefox page browser.
Oh, I see. Because
Control shift is.
I think automatically there was a system instant. Like they're not actually allowed to. They're like this. So they're not collected. So you're not. There it is. There's the actual one. I'm not. See if you're all. That actually might be what it is. So it might have been connected to one of the resistors, but not the other one. So that's actually a reason why you would want this. That's
All motion shots. Your.
I mean, in browser, the maps matter.
For example,
Depends. Also, what the heck happened to my capacitor? There it is. Okay. It doesn't matter. So you know how we label the pins pin 1 and pin 2? If it does matter, we can just like make a note in our head when we're designing the circuit. We will connect the positive end to pin 1 to negative. For example, this 5-5 timer, definitely the pins matter, right? So we've labeled them as such, and then the orientation. But for components that don't have that orientation, like the resistor, we didn't think about it. So then there was really no issue. Does that make sense? It's like then if it does matter, we will make a note of it, and the designer of the schematic will design it. And also, as another note, where the capacitor we're using is non-polarized, so you can flip it around. It's only like the electrolytics are the ones that have that polarity. You flip it around, it explodes. So that's fine. Okay.
You said the dot's supposed to be on the outside, right?
That's correct. All right.
Hey, Ryan, we found something critical to this project.
What's
There's actually a 9-volt battery holder with the plug that goes into this jack, and the component listing is literally just called 6.7 in DigiKey. There's no name or any other
it's
part.
you put in the Discord like
Oh, 6.7.
you put in like the project for Discord. Is that why you pinged me?
No.
It's some okay. Ooh, you guys can see the project or Discord. It's crazy. Oh, if you became a board member on IEEE, you could also see the project or Discord. Ooh. Join today. We need yeah, if you guys are interested in leadership positions, I think next year a majority of our board is graduating. So our elections this year will be very spicy. So if you're interested in, doing what we do, doing these projects, doing these workshops, it's really called 6.7. This is a great use of our time. That's great. Who doesn't know the 6.7 mean? It'd be really fun. You make no sense. Like, what are these guys talking about? All right. Who's still working on this? Who still needs this? Circuit up. All right. I think we're good then. All right. So congratulations, everyone. We have finished the first step in PCB design, is determining where the parts are going. Now, I want to introduce the last thing really quickly, but I know we don't have enough time. It will be actually making the footprints for each part as well. So it's just as fun. But we'll be continuing that next workshop as well. But I'll just go over one of them for now, just so we have so we know what's going on. So if you guys recall from my presentation, a footprint is how the component actually looks like on the PCB. So no, we're not drawing a squiggly line. It's just the holes where the PCB is going, or sorry, where the component is going. So for a through-hole capacitor, or sorry, a through-hole resistor, such as this one, you can imagine that the footprint is just going to look like 2 holes. Are we convinced that's all the footprint's going to look like?
It's just the silk screen in the designator position.
Sure. All right. We'll put a box around here that's silk screen, and we'll label it R1. That's what the footprint looks like for that. Because all you need are 2 holes, right? So if we look at the data sheet, which I was able to open up, we can see the size of the actual resistor. So we can space these holes out properly. So I'm looking at, I think we're looking at a CF12 resistor. So if we look at the code here, CF, the length A, so the length A is going to be, so we're going to use millimeters, 3.3. And then we're going to have a little extra width there. Maybe we'll add an extra B there. So 3.3 plus 1.7 on both sides. And then anyone have a calculator? What's this number?
And I'm pretty sure it's 12.7, but I don't have a calculator.
Wait, 3.3 plus 1.7 plus 1.7. 6.7.
Oh, wait, yeah. I don't know.
All right, so let's now go not to the schematic library, but the PCB library. Now we're making the footprints. So there's a document called PCB library. We're in that. And if we go to panels, PCB library on the left there, that pops up another library. We're going to be making these footprints. But what Altium has is really nice because while we weren't being very precise on the schematic symbols, because we don't need to be precise, these ones we need to be precise. So what they have for us is a tool, if you go up there to tools, called Footprint Wizard. So it's a tool that will build a footprint for us. All right. So if you click on that, it'll pop up have a pop-up that'll show us the footprint wizard. Can we get to this? And everyone, I'll give a second for everyone to get to the screen. Oh, wait. Somebody talk about? No, you're good? Yeah. Okay. Who's not on this screen right now? Okay, you got it? So around the PCB library, the tools, footprint wizard. Okay. Now, if we hit next, they'll actually give us a couple of components that they have this wizard for. So once you know it, they have resistors. So we're gonna click on resistors. And let's do millimeters, because I think this was in millimeters. Yeah, so we're gonna do millimeters. So resistors, millimeters. And then next, they're gonna ask us what kind of technology are we using? Are through hole or surface mount? Survey says, what are we using?
Surface mount.
You want to attach this on a surface mount? It's possible, but we're gonna do through hole. All right. So next, they're asking us the size of the hole, the diameter of the actual hole. So for that, we can actually go back to the schematic document, and it's telling us this length D is the lead diameter is 0.4, plus or minus 0.08. So what does that mean? It means our hole still needs to be able to hold the maximum width of this lead. So maybe not 0.4, but 0.48. Let me see if they have an actual recommended footprint. If they have one, that'd be fantastic. Okay, they don't. That's all right. And so 4.8. So we can do 4.4. Sorry, 0.48. Go back up here. Yeah, 0.48. And then these outer pads are what's going to be available to solder on the resistor. So when we place the resistor into this hole, there's actually going to be an outer flat area where the solder is able to connect from the PCB onto the pin. So rule of thumb is usually double the diameter of the hole, but it actually doesn't hurt for it to be bigger because more surface area means it's easier to solder. So we can actually just leave it as that 1.2 millimeter, and we'll move on to the next one. Now that's where the number we came up with comes into play. The distance between the centers of the two holes should be, what would we say this was? 6.7? 6.7. All right, 6.7. All right. And then this is for the sub screen. We can just leave it as is. That doesn't matter. Or when we can name this resistor. Well, I mean, we only got one resistor, so we're gonna name it resistor. All right. And the wizard has created a footprint of two holes and the silk screen. Now that's a kind of weird silk screen. I don't know what happened, but we can now adjust the component from here. Maybe have like a box. That was it? What?
It was really jank how not only did it put a line down the middle, but it split the right side.
Yeah. That's really funny. I don't know. So that's the footprint for the resistor. And what's really cool is that you can actually see this in 3D. Okay, maybe it's not that cool, but you can look at it, and that's what it looks like on the piece. So actually, this will come in useful once we start um, putting them onto the PC. But that's the footprint for the resistance. Two holes, and we can slot the component into it. And the gray area is the exposed copper that'll let us solder it on. Cool. It's really handy with the wizard, right? Let's try another one. Who wants to try another one? We have time. All right, let's try another one. Actually, let's do it at 555. All right, yeah, let's do it. It's 555, right? So we'll notice that they're called the package that they're using is called, does it say? Oh, it says on the here though. It's that. We're doing DIP, dual inline package. 8. So you'll notice it's 8 through hole pins. That's, they're through holes. I don't know what else to say about them. But the wizard has a thing for that as well. So again, we're going to go to tools and then footprint wizard. And then we're going to hit next. And this time we're going to click on this. DIP, dual inline package. Hey, they've got it for us. How kind of them. I think we are going to use, actually, I wonder if they've given us a PCB layout for us. I wouldn't be surprised if they did. Okay, that's not what I was looking for. Okay, I don't see it. All right, so dip, and we'll do millimeters again, I think. Next, I think these can stay default. This is really annoying where like they don't have the layout. You've got the layout here, and tell me what the dip layout is. Tape and reel to, oh, there it is. Nice. Let's see. Here it is. That is the dip package, plastic dual inline package. So we're looking at the length of the thickness of the diameter of 0.010. I believe that is already giving us units somewhere. It's very important to have units. All linear dimensions are in inches, parentheses, millimeters. So the distance between the pins is 1 inch or 0.1, sorry, is 2 millimeters or 0.1 inch. Well, thickness is 0.010 inches or 0.25 millimeters. So we can give them a thickness of 0.25 millimeters. That seems wrong. Yeah, there's no. Usually these things they give a recommended board layout. Wait, it's right here. What am I doing? No, but that's the surface mount level. What the heck? Fed up. Yeah, dip dual inline package.
Yeah.
Let's see.
You can probably just look
Right.
at the standard 8-pin dip
Yeah,
recommended layout.
Probably.
For any IC.
8 dip layout. PCB layout. PCB print. Okay. Actually, we just actually let's just add a point. Make a 0.3, sure. It's fine to have the holes bigger than the actual pin itself. Let's just do that. And then we're looking at the distances. How do they not have a pin layout for dip? This is diabolical.
They're a tenth of an inch apart next to each other.
Oh, wait, no, wait, we saw it already. Yeah. It's actually right here. Yes. It's a tenth of an inch apart. Tenth of an inch apart here, or 2.54 millimeter. And that distance is at maximum 10.92 millimeter. That's just me panicking here. So 10.92 millimeter max, right? And 2.54 millimeter here.
Maybe you want to do less than 10.92 because that's if the legs splayed all the way. That's the max. You can actually push them in more, right?
Yeah, it's true. Well, it depends how we're setting it into the PCB, right? We're just soldering it in directly. I think it's fine to leave it like that because what we don't want is for it to be too narrow. Because then what happens is now you have your pins kind of rubbing against the package. That's not very good. All right. So hit next. With so like this is just the outline. Number doesn't matter. Oh, do you guys still need this number here? 2.54 millimeter, 10.92 millimeter. 2.5. So 1/10 of an inch. And then this is supposed to be an 8 dip package. We're gonna call it 555 timer. Hit finish, and that actually looks pretty good. That is the footprint for the 555 timer. And you'll notice what's nice is that this outline has a little notch at the top, which marks the top of that component, that chip. So if you look at the chip there, they put a dot at the top to mark where pin 1 is. So when you flip it over, you don't get confused where pin 1 is, right? Same deal, they just have a notch right there to show where pin 1 is. All right, and that's actually making the second footprint. All right, go ahead and that will be it for today. Go ahead and hit save on your PCB. So give it a second. Go ahead and hit save on everything, actually. And what you're going to want to do is save everything else as well. Yeah, let me see where that save. Okay, there it is. Next week, we'll be going over making the rest of the footprints. And we'll also be talking about how to lay them out, best layout practices, and like getting it manufactured. So thank you all for coming to today's workshop. Give yourselves a round of applause for coming here on a Friday and putting in the work. And yeah. So if you haven't already, go ahead and join our Discord server. That's where we're going to announce everything, including next week's workshop. But it will be in the same room next Friday. Yeah. Another side note is that the PCB that we're making today, this buzzer circuit, we'll be getting it made, and you'll be able to build it at our soldering workshop. So if you wanted to take the circuit and now actually use it to make a bunch of noises, we will be having a soldering workshop on November 21st to basically learn how to solder. So if you want to actually have the full design process, including literally soldering it together, come check us out. Again, thank you all so much for coming. If you haven't already, please sign in. Thank you. What? Oh, yeah. We have the commitment form still open. Yeah, sure. Yeah. Oh, yeah. And I know a lot of you might be here because you're interested in the projects, but if you're not and you're still interested in our projects, let me go to the server. If you go to signups and forms on the bottom here, this is the form that you can mark if you're interested in being a part of our 3 projects. We have the FPGA project, the keyboard project, and the micromouse competition. So if you're still interested, they haven't started yet. We have sent out emails, but if you're still interested, we'll fill out this form. And
Also, the micromouse event, if you guys have any questions, you can shoot me a message. You're on the Discord, it's my name. Do you have any questions? Just, I was different. Do you have any questions? Just shoot me a message. It's gonna be like the donut. You can probably see it somewhere. I don't know. But like, shoot me a message and I'll let you know. The times haven't been decided yet, but fill out the when to meet and we'll just forward you to the email. So we'll know what the best time is. So that the people that are most interested in attending the workshops and participating in the project get it so that it aligns best with their schedule. So please fill out the forms. Thank you. That's like, cool.
Thank you all so much for coming. Oh, and if y'all want to buy boba cards, I also have free boba games.
So my triple B day is still on, so many of your big societies have free membership. So you can add that as well if we get next year.
Oh, I have them on me. If you want to buy them, it's $5 cash. But these cards, these cards, you can use them at any 7-Leaf store, and they let you get 3 buy one get one free drinks. Actually, let me close them. Stop share. Stop recording.